Hello everyone. I am Ayush and welcome to the RECollect sessions. Okay, so through this series we will cover the fundamental concept and important topics that are essential for competitive programming. Okay, so there are many topics listed in which we will discuss dynamic programming, graphs, trees, recursion, backtracking, game theory, and many more topics. Okay, so you will just have to be with us so that you can grab the information and you can strengthen your understanding of these topics. Okay, so let's start the class. Okay, and is there any doubt? Then you can ask me, or if I'll and then I'll start. First of all, am I audible, guys? Hello. Okay, so let's start the session. So today we will discuss the advanced recursion and backtracking. Okay, so in which we'll just what are we going to learn today and recursion, backtracking, and important questions. Okay. Oh, first of all, let me share my screen. Sorry for that. Sorry. I forgot to share my screen and I'm speaking. Sorry, guys. Sometimes it happens. So my screen is visible to you, guys. Okay. Let's start again. So we'll discuss advanced recursion and backtracking. Uh, some topics are listed like recursion, backtracking, and then we'll discuss the important questions. And so I'm going to explain it on the board, and then we'll see. We'll see the PPT. So what is recursion? What is recursion? So recursion is nothing but a function which calls itself. A function which which calls itself. Okay, like you have saw many functions, you have built many functions, you are solving many more questions. So while solving, you definitely have made many of the functions. So the basic structure of function is what? This is your function name. Here you will pass the parameter, and there you will write the body of you know the function. So in which if we will call the same function inside the function, like fn again, so this will repeat the function again and again and again and again. So you will, if you write this statement, if you'll write this statement, then what happens that it will create the same functions multiple instances. It will create the multiple instances of same function. So you are just repeating the process like you used to repeat in the loops. Like when we use loop, n minus minus, then whatever will be here, you just repeat the process for n times, and you are also doing the same thing. And if I'll have to show you with the drawing, like if this is your function, if this is your function and here you are calling it again. So when you call it again, you whatever will be written below of that line, that will not execute. That will not execute until this function finishes, until this line finishes executing. So first of all, when your pointer will reach to this line, when your execution will reach to this line, it will call the same function again, and it will build the same function. It will create the another instance of the same function. Okay, and then it will again start executing line by line, and when it will reach to this line, it will again create the same instance. It will again create the same instance of the function. And and again this thing will happen uh, multiple times. If you will not write the base case, it will go till infinity. you know it will go till infinity. It is just go on. it will never stops if you will not write the base case. Okay, so for stopping, and you always want to stop your recursive solution, because if you want if you want to stop the recursive solution recursion, then you definitely won't get anything from here. So you have to stop your solution, and for stopping, like if you want to stop here, then you will add some kind of base cases, some kind of base cases, and for which, you know and base cases, so that you will just return from here. For returning, like you have to return to the these instances again, so that you can execute the another part that is remaining. Okay, so for this you have to return, and for returning you need a base cases, and you will just draw a line like this is a line, this is a line where you won't go to this part, you will just remain to the left part also. Okay, so for this you will have to write a base case, and this is just a drawing representation, so that you can understand it better visually. So that's what the base case. For stopping the recursion, not stopping, for returning from a point where you don't want to go, just add a base case. So this is about the recursion, and I'm going to explain it by example. Like we'll take an example that if you know how to print the 1 to 10, you all already know that, I don't have to ask you, but you know how to print 1 to 10 by a loop. You can print, while like if you have to print 1 to 10, you will store n equal to 10, or n equal to 10, and you will start for loop to 1 to 10, and you will just see out I from here. Okay, so you can do this. This is your for, this is your for. Okay, so you can do this thing, but how you can do this? Via using recursion. You can do this thing using recursion also. So I'm just going to explain it by this. Like you can, like you will write a function, and you will take where you want to go. Like you can print 1 to 10, 1 to 11, 1 to 100. So you just have to pass this value, and you will just able to print the 1 to n. Okay, so you will just pass a parameter for it, and for this what you will do again, because you have to print 1 to 10, and I will just write it down, and then I will explain it to you that how it's happening. Okay, so first of all, you will just you will subtract, and you will call this function again. You will call this function again, and you will, when it becomes zero, because you don't have to go you don't have to go 0 minus 1 2 minus 2 minus 3. So you don't have to go this way. You just have to decrease till 1. You just have to decrease till 1. So if you will add a base case, if n equals to 0, then you will return from there. You will return from there. You don't want to go this way, so you will return from there. And if it is not, then you will just decrease the value till it becomes a 1. So when it becomes 1, you will just start printing it, and this is your end. So this function will print 1 to n, and if n equals to 4, then it will print 1, then gap, then 2, then gap, then 3, then 4, and then gap. So this will print this. And let me show you how it's happening, how it will happen when we'll call this function in the main. Okay, so I just draw some of the instances of the same function, so that you can understand it better. Like the same function that I have wrote there, I have just written it here. uh, so let's take the n equals to 4. N equals to 4. Okay, n equals to 4 here. N equals to 4, and then when you will when you will what you will do, when you will call this function in main, so the the execution pointer will pointer will go from main to the that function. So it will keep the track of it. For keeping the track of what, from where you where you are going, or where you are going, you will the compiler will keep the track of it. And how it will keep the track of it? It will just, it will push this it will keep the pointer of main in stack. We use stack for keeping the track of whatever instances that we have. Okay. So we just push this main into this, and then the pointer will come to here, and then we'll see what is the n value. N is equals to what? 4. So it will check, it will check whether n equals to 4, n equals to 0. So it will say no. So it will come again here to this line, and then it will call the same function again, and it will go to here. And then when it will be going to this, and when it will going to this function, this instance, the n value becomes the here n value becomes what? 3, because we are passing n minus 1, not n. So it will become what? 3. And then it will again check whether it is 0 or what. So no, it is not 0, it is 3. Then it will again come to this line, and again it will just go to here, and n value will become for here too. And then the function will come here, it will create another instance of it, and then we will be here, and it will again check whether n equals to 0. So it will say no, it is not, it is 2. Then it will again come to here, and then it will again create another instance with the value, with the parameter what? 1. With the parameter what? 1. And then it will come to here, and then it will again check whether it is equals to 0. So it will say no, it is not. So it will again come to here, and then it will check whether it is equals, it will again create another instance, and it will come here, okay, with the value what? 0. So now it becomes 0. So it will check, it will check whether it is equals to 0 or not. So it will, this condition will be true, this condition will become true, and then it will return. It won't, when it returns, the function ends there. Whenever whenever return, whenever the execution of return happened, the function ends there. So for in this instance, because this return statement has been executed, so this function has been ended there, and it will return to again to this line, okay, with nothing, because this is void function. We haven't returned anything, with the we haven't returned any value. Okay. So it will again go to the previous instance. Okay. We again go to the previous instance, and we will check. So we will check the, what is there any line, that we have to execute for this instance. So it will say yes, we have a line, we have to print this, value, print this value, whatever is there. So the value of n is equals to what? 1. So it will print what? 1. It will print 1. So whatever will be the output, I'm writing it here. So it will first print 1. Okay. And then because you here because this function ends, so it will again return, and you will go from here to here. You will again go from this instance to this instance, and again, because this line has been executed, and now you again to this function, this instance. So the remaining line is this, what? Remaining line is this. So for this instance, the value of n equals to what? 2. So you will again print the value 2. And then you will, because this function ends, this function finishes, so you will again come to here, and then for this instance, n value is what? 3. So you will print 3. And then you will, because this function finishes, then you will again come back to this instance, and then you will again check what is the n value? 4. So you will print the 4, and the function ends there. So a function ends there, and you will again come to here, and whatever will be the other lines that will execute, but you will get your output here. Okay. You will get the output here. So this is how, the recursion of flows when you call a function. Okay. So this is what the happening. So I'm going to explain it again, okay, because I haven't draw the recursion stack. Okay. So I have to explain it this way also. So whenever because your pointer goes from this to this, you will push this one into the stack. Okay, so now your pointer goes this from this instance to this instance, your pointer moves from this instance to this instance. So what you will do, I'm just calling this instance A, this instance B, this instance C, this instance D, and this instance E. Okay, so when pointer moves from this instance to this instance, then it will push A to this call stack, and then again you will go to this instance, then you will push this into the stack, and then you will again push C into this stack to, while you were going to the D1 D. So you will again push D while you were going to the E, you will again push B. But here you won't push anything, because you will there you won't call any other there you won't call for this statement, you just return from here, you will just return from here. That's why you don't need to push E to the call stack. So what you will do, you will just return it from there, you will just return it from there to go to this function. Now because D is finishes, because whatever would be how you will keep the track. Now this is the part that you have to understand it. Like, you will just pop out the top one, you will just pop out the top one, and and this is the way that you will get this is the way that you will get the previous instance. So you will pop out this one, and you will go, you will it will be not there, it will not be there, and then the top value will be there for C. Then when the D finishes, then you will come back to this function, this instance. So the internally what happens this, you will pop out again C, and then you will perform the operations on it, and then you will pop out B, and then pop out B, and then you will perform the operations on it, and then you will perform A, and then you will perform the remaining operations on it, and then you will return back to the main, and then you will pop out the main. And when you will pop out the main, then you will pointer will be here, and then you will execute the remaining statements. So this is the way that the recursion flows from one instance to another instance. Okay, so uh, so if till now you have any doubts, you can ask. Have you understood the the flows of recursion? Guys, you can ask any questions if you have. Okay, so let's move on to the PPT. That uh, So what is recursion? Recursion is a programming technique where a function calls itself to solve smaller instances of the same problem. It helps break complex problems into simpler problems. So yes, where here what we are doing, we have also here what we are doing. What we were doing, that we always used to divide the problems into sub problems. We have first divided into four, and then we have first divided into three, and then for two, and for one, and then for zero. So we have created multiple instances, and that is what you are dividing the problems into sub problems, and by solving the sub problems, you are getting your final answer. Okay, so by creating the instances, you are dividing the problems into sub problems. Every recursive function must have base cases. Yes, this is must. For stopping recursion, you need to add base cases, and recursive cases calls itself with a smaller input. Okay, so and the general structure of your recursion is this. And I just and I had shown you when I was discussing. So you can see, here void solve parameters, and there you have added the base condition, and then your remaining statement would be there, and then you have called the smaller problem with the function again. So you have called the function again. Now, why learn recursion? Recursion reduces length iterative code. First, reduces length iterative code. Okay, and second one is useful for tree and graph algorithm. And you will see, when you will be learning trees, and will also cover those topics also, trees, graphs, and will also cover the dynamic programming. And there you will see, that recursion is how much helpful for you to solve the uh, to solve the problems. Okay, so helps solve divide and conquer problems. Yes, yeah, it also helps in dividing the problems into sub problems. This also divide the problems. Divide and conquer approach is also divide the problems into sub problems, into two halves, and then again two halves. So in this way, this happens. So we can also use their recursion, and then forms the foundation of backtracking and dynamic programming. So I haven't told you about the backtracking. So let's get back to the screen. So while we were coming back to D to C, and then C to D B, and B to A, we were doing what? We were backtracking. First, you reached to so first you had reached to somewhere where the base case has been executed, where base case has been found. Then you will return to previous instances, so that so that you can find out the answers for it. Okay, so while you were returning, what you are doing, you are backtracking, you're tracking by backward, you're tracking everything backward, okay, in a backward way. So that is what the backtracking means. That is what the backtracking means, so when you are going from D to C, from C to B, B to A, and then A to main, then what is this? This is your backtracking. So is there any doubts, guys? Any doubts? Okay, let's move on to the next topic, which is how recursion works. So recursion flow that I have discussed. Function is called, work is performed, function calls itself, and then calls continue until base cases is reached, and then when base cases is reached, function return by one, and that is what the backtracking is. And that's it. So an important concept called stack. So every recursive call is stored in a memory. Yes, and this why this happens, because you have to get back to this instance again. And for this, how compiler will be understand that in which instance you will have to go if if another instance is finishes. So for this, it keeps the track of the each instance in the stack, and it will pick the because you will have to pick the top one again and again. So for this, which data structure you can use? You can use stack. Okay, and we have discussed stack in previous classes, and if you will have attended the class, you will definitely know about it. What is this? So it works on the principle of LIFO, last in first out. uh, and then when the base case is reached, calls started returning. Yes, that's what the backtracking is. So if you need, I can give you some more examples. Like, okay, let's discuss it. Like, if you I have shown you the code of, you know I have shown you the code of how to print 1 to n. Okay, how to print 1 to n by using recursion. Can you tell me how to print in reverse order, like uh, 5 4 3 2 1? Can you give me a suggestion that I can, I can just change in one line or two line or whatever, so that I can get my answer? You can open your mic and uh, you can tell me. Like, did you understand the question? What I'm just asking you, how you can print the numbers in reverse order. Okay, I'm going to tell you if you are okay. So for printing in reversing reverse order, what you can do, you can just, whatever this line is, if wait a minute, whatever this line is, if you will just, if you will just keep this line before calling an another instance, then it will print all of the numbers in reverse order, because you are printing the numbers, and then you are doing what, you are just calling the another function. So first it will print 4, because you have just you have just, you have just uh, keep this line before the before this f of n minus 1, and for everyone. So if you will, this line is now here, and this line is now here, and this now is line here, sorry, this line is now here, and this line is now here. So for this, if you will do this thing, only one change is required to get the number in reverse order. So you will be able to print 4 3 2 1. Okay, so this was it. And if you want to print the if you want to, if you want to print the sum of, all of the numbers, like n is there, and if you want to print sum of all the numbers, then and you want, if you don't want to take any other variable, then you can just uh, keep the return type as int, keep the return type as int. And if n equals to 0, you want 1 plus 2 plus 3 plus 4 plus till n. Okay, you want to add this number, then what you can do, you can just, if n equals to 0, then you can return. And for this, what you can do, you can just return n plus f of n minus 1. So it will again call this function before return, before summation. When it will end, it will end when this calculation has been finished. So it will operate from left to right. So when it will reach, when it will operate, when it will calculating this one, so it will first call, and the execution will stop here, and then it will go to the next instance, and then next instance n minus 2 n minus 3 n minus 4, and then till 1, and then 0. And when it will become 0, then it will return from there, and then start adding from the behind, 1 2 3 4 5 6 7, and then start adding from there. And it will and then finally you will be able to get your final answer with this way. So this is uh, this is for the, if you want to add the all of the numbers via using recursion. So now let's talk about the time complexity for the recursion. So let's talk about the time complexity. So I have drawn, like, first of all, what time complexity will be for this function, for this loop, while n minus minus. What will be the time complexity for this? Guys, tell me, what is the time complexity for this? Okay, so the time complexity for this will be equals to big O of n. Okay, so because you are because you are what, you are performing the operation n times, whatever will be there. If it is big O of 1, then the time complexity of this will become big O of n. Okay, so sorry, I haven't showed you the screen. So the for the this time complexity will be equals to what, big O of n, if the whatever will be the body is taking constant time. Okay, so Okay, so if it is this, then I have shown you the call stack where you are calling the you are making the multiple instances, like here what you are doing, you have created the multiple instances, like in for a your n value was what, 4, for here n value was what, 3, here 2, here 1. Okay, so and if this value was a very large value, like it will be 100 and 2000 10 to the power 5, something like that, then you the then this stack then this stack would have taken the space of what, 10 to the power 5, if the n value n equals to what, 10 to the power 5. So this stack, if this stack is storing something, then it needs a space. So the to store this, this n values, for if there are multiple parameters, then also there will be more uh, memory used. But for this, I'm telling you that for this, n equals to 4, n equals to 3, n equals to n equals to 1, and if the number is very large, then then the time complexity will also be here equals to big of n, because you are using a stack, and in this stack you are uh, you are you are just holding the each functions, you are just holding the each instances, like a b c and d, you are just creating a variable and again and again locally, because you are just creating this and local. These are the local variables. If you have passed this as a reference, then then the time complexity for this would be equals to 1. But but because you have passed this as a value, then the time complexity will be equals to big of n, because I just told you that you have just initialized 4 variables, and this 4 variables will be equals to 4 variables size is equals to array of size 4. So if n variables you have initialized, then it is equals to n array of n size. So that's what I'm telling you. So if for this, the time complexity is big of n, then for this one also would be equals to time complexity big of n. So in this way you can find out the time complexity. Okay, like for this question is this, and for for different recursive relations, there would be more time complexities. like like for Fibonacci numbers, what is Fibonacci numbers? Like if the number if we'll add the previous two numbers, then we will be able to get the next number. Like and the base cases for it base cases for it is 0 and 1. Like this is your t0, this is your t1. So if you'll add this, then you will get the next number, which is what, 1 again. Add this, you will get the next number. Add this, you will get the next number, 3, and then 5, and then 8, and then 13. So this is your what, Fibonacci number. So what you are doing, you are just adding the previous two numbers. So tn equals to tn minus 1 plus tn minus 2 for n greater than equal to 2. So this is your recurrence relation and recurrence relation. So if you repeat the process, you will be able to get the nth term. So this is what you are calling, like your if let me explain it to you again. Like if you need the sixth term, if you need the fifth term, okay, if you need the fifth term, then what you will do, you will just what you will do, and you know that the t0 is equals to what, 0, and t1 equals to what, 1. So t5 will be equals to what, t4 plus t3, and t4 will be equals to what, t3 plus t2. T3 will be equals to what, t2 plus t1, and t1 equals to what, t2 equals to what, t1 plus t0. Now you know these two numbers, so you can find out t2, which is what, 0 plus 1 equals to what, 1. and 1 plus 1 equals to what? 2. And then 2 plus 1 equals to what? 3. And then your T3 is 2 and your T4 is what? T4 is 3 and T3 is what? 2. So 3 plus 2 what? 5. So your fifth term is your 5. So what you are doing, this is your recurrence relation, and you are repeating the process to get the nth term. So you this is what you are doing. And uh, if you write the recurrence recursion solution for this, what you will get like fn for this Fibonacci numbers. If you want the fifth term, the solution will be what? If you want the fifth term, then first what you will do, you will just decrease the value f of n minus 1 plus f of n minus 2. Why this? Because your recurrence relation is what? This. You will have to you have to, for getting the nth term, you have to add previous two solutions. So you are just creating the smaller sub problems here, and you will return this thing. And for this, what was your base case? If n equals to 0 or n equals to what? 1, then no. If n equals to 0, sorry, if n equals to 0, then return 0. And if n equals to 1, then return 1. Okay. So by this way, you can get the nth term for nth terms value for Fibonacci numbers. But you are calling two times. So if I'll show you the what? Recursive tree. So you will get the better idea. Recursive tree is nothing but we have drawn here the this stack thing. By and this way you will get the better idea that how the flow is going on. And if you will just rotate this, if you'll just rotate this way, then you will get the recursive tree. Like if a, b, c and d, this is what, from a to, you will go to b and then go to c and then go to d, and then you are coming back again and again. So this is what your I'm just drawing it in a way that trees are drawn. Okay. So so first your call was what? F of n. And then because the function because the function because there is an operator plus, it will execute from left to right. So first it will execute this one. For every instance, first it will execute this one. So it will go f of n minus 1, and then for f of n minus 1 it will go f of n minus 2, and then for f of n minus 3, and so on. And when it will reach to f of 1, because when it won't return till 0 to 0, because you are just decreasing one by one. So when it will be equals to 1, it will just return it from something. So for uh, it will return from here. Okay. And then it will come here, and then it will go back to here. And when it will be here n minus 3, then it will, for this one, it will create another instance which will be equals to what? Because from here you just have created f of n minus 4, but you haven't created any other thing, like you haven't created f of n minus 3 minus 2, f of n minus 3 minus 2, because here was minus 1, and here this is what? F of 3 and minus 2. So, and now you will add these two values to get the f of n minus 3. So what I'm telling you, for then you have two choices. you have to create the f of n minus 1 and f of n minus 2 for each values. Like if and like in this problem the n value was what 5, so it will be f of 4, and then f of 3, and then f of 2, and then f of 1, f of 1, and then it will go back to here because it will return what 1, and then it will again call f of n minus 2. So 2 minus 2 will be equals to what 0. For 0 it will return what 0, it will return 0. So it will add these two values and get the answer for it, and which is what, which is 0 plus 1 equals to what 1. So so for this it will go here, it will go again here, and it will again calculate f of 3 f of n minus 2. So 3 minus 2 will become equals to what 1, and then f of 1 minus 1, which is equals to f of 0, and it will return like no, because you have already reached to 1, then you have reached to the base cases, then you have reached to the base cases. So it will just return it, it will just return from here, it will just return from here, and which is what 1. So this returns 1 and this returns 1, so for this one you will get the value as 2, and you will again come back to here, and then you will again you will again call the function again. You will for n minus 2, for n minus 2, so it will be f of 2, and then it will again call f of 1 and f of 1, so it will return here 1, and if because it reached to 1 it will return 1, and then it will call f of 0, f of 0, and then it will return, yeah, from here 0. So f of 2 you will get what, you will get 1, you will add these two 1 and 0, then you will get 1, and then you will return 1 here. So for this you have created these two for every n values you are creating, for every n values you are creating two, because you have to small uh, you have to take the problems into two some smaller sub problems. So we have just created these two, and then this will go on till 0 to 1. So what I am trying to say is, for every n, for every n you have two choices, you have two choices to break the problems into sub problem. Like you have, if the one, if you have n if n is equals to, if you have n numbers, if you have n numbers, then 1 2 3 4 5 6 7 8 till n, then for every numbers you have what, two choices, two choices, two choices, two choices. So and for this number n you will also have the two choices to break the problems into sub problem, and it will go on to the, if you will break for this, it will go on to the either 1 or equal to 0, either 1 or equal to 0. So what I am trying to say is that you will have you will have to multiply each values, because the problem is not finished till now. You will definitely have learned this concepts in the permutation combinations. Like you will have to multiply all of the choices to get the answer. So 2 raised to the power m, because you have break you have n choices, you have n choices for, you have two choices for n values. So the time complexity will become what, 2 raised to the power n for this problem, because for everyone, for every function, every instance, you have two choices. So the time complexity will become what, 2 raised to the power n. I've just derived the how it become, how you can solve the you know uh, how you can uh, solve for time complexity. Okay, so if you have any doubts till now, you can ask. Okay, then let's go back to the PPT. Like like you can see here, uh, Time complexity measures how the running time of an algorithm grows as the input size increases. Yes, we have discussed about the time complexity in previous classes. In recursion, it depends on number of recursive calls made, okay, and work done inside each cell. Work done inside each cell. So this is what the time complexity is. Like, because I have considered that in every, what I have considered, because here is nothing in the body. Your time complexity is what? Big O of 1. So the final time complexity will be equals to what? Big O of 2 raised to the power n into big O of 1. Big O of 1, which is equals to what? Big O of 2 raised to the power n. Because the inside work done is what? A big constant. Okay, that's what it is saying. So if your recursive relation is if your recurrence is recursion is f of n equals to if this, then your recurrence relation will be equals to tn plus tn minus 1 into big O of 1, and time complexity will to what? Big O of 1. And this you can also, and this is the recurrence relation of arithmetic progression. And for this one, will the recurrence relation would be equals to this, because for tn, f of tn, you can say tn or fn, whatever you want to say. Tn equals to tn minus 1 plus tn minus 1, and work done of inside the function is what? Big O of 1. So the time complexity will be equals to what? Big O of 2 raised to the power, and that I have discussed right now. Okay, because here also you have two choices. Here also you have what? Two choices, n minus 1 and n minus 1. Okay, you are for every n you will call two instances for the same n. That's why for every n you have two choices, so you will multiply all of the choices, you will again get the same answer that I have derived. Okay, and then time complexity analysis is number of choices, and depth of recursion. So depth of recursion, or you can say the depth of recursive tree, because and in this in this solution, in this recursive tree, the depth of the tree is what? Depth of the tree is what? N. Because every time is where you are going, n minus 1, n minus 2, n minus f of 1. So n is moving from 2 1. So the depth is what? Depth is equals to n. So the number of choices is 2, and depth of recursion is n. So the answer will be equals to what? 2 raised to the power n. You can also see this way. And here for this, the recurrence relation will be equals to tn equals to tn by 2, because every time you are dividing it, dividing the number by 2. Okay, time complexity will be equals to what? Log of n. And guys, tell me, you want to see the derivation for this one, how it is coming? Okay, then I'm considering you all know that, so the time complexity for this one will be equals to what? Big O of log of n. And for this, big O of n. And for this, I've discussed it. Sorry. And time complexity analysis in recursion and backtracking. So this is your quiz time. You can answer this question, guys. You have a grid of n cross n, and possible choices are 4. You can go for each from each cell to either up, either down, left, right. You can move in 4 directions. So what could be the time complexity for this question? Tell me, guys. Okay, I don't think you will tell me. So because you have a grid of n cross n, n cross n. Okay, so this is n, there, there are n cells and there are n cells. Okay, there are n columns, there are n rows. Okay, so if you will be here, how many times you can go in the right direction? N times. Okay, n times you can go. And if you will be here, how many times you can go up? N times. Okay, if you will be here, how many times you can go left? N times. Okay, and what's remained? If you will be here, how many times you can go, come down? N times. So for each possibility, for each recursion, sorry, for you have you have four choices. You have four choices, but how many times? The depth will be what? The worst case, in worst case the depth will be what? Your n. So the time complexity to what? 4 raised to the power n. The time, this will be time four choices and depth, or I can say the you will create n times. In the worst case you will create n times the same instance, so the time complexity will be equals to what? 4 raised to the power n. And this is your homework. Think about when your time complexity will be factorial. I will discuss in the next. Okay, think about it once. So summary of time complexity for binary choices. Binary choices, it will be 2 raised to the power n. Three choices, 3 raised to the power. Four choices, 4 raised to the power n. And I have shown you this thing. This permutation for the, because let me discuss 1 2 3. And because if you have to find all of the possibility, and you will have definitely learned this concept then in the permutation combination, that to find out the number of ways, you will just have to take the factorial of the total numbers if all are the different. So because here all are the different, so the total number of permutation will be equals to what? N factorial. So if you have n factorial total number of ways, so finding all of the possibilities like 1 2 3, 1 3 2, 1 2 3 1, 2 1 3, 3 1 2, 3 2 1, you will have to create at least what? For these three numbers uh, you have to create at least n factorial, sorry, six instances, and six is equal to what? 3 factorial and 3. And if the number is 3, then it is, if the number is n, then n factorial. Okay, so this will be the time complexity for permutations, and if you want to derive the all of the permutations. Okay, what is backtracking? Explore one possibility completely and then revert back. So that's what it is, what the backtracking is. When the base cases is reached, you are just backtracking. Okay, you are just backtracking. If there are many choices, if there are remaining choices available, then you will explore to that one also. And if there are not, then you will again backtrack to the previous instance, and then previous to previous, and this way you will just backtracking it to get the the main. Okay, when to think for it in a question where we need to explore all possibilities. Yes, because the recursion is what? You are just exploring all of the possibility, whether it is, sometimes you will find out that it is not possible, and that's what the base case is. That's why you applied the base case, where you don't want to go there. Yes, you will apply the base case, you will return back from there. But even if you will apply the base case, you will get some the random solutions for those, but you will have to you don't have to think for it, you will just have to think for the best solution. Okay, most importantly, the constraints should be lower as well to allow it. Yes. And generic backtracking template is For all choices, choose, solve, and then unchoose. That's what we used to do. So this is from my side, guys. And now Sujal will continue from here, and he will discuss the problems that we have to discuss. Okay, so from here Sujal will discuss. But if you will have any doubts till now, you can ask me anything, guys. Please ask. Okay, then now Sujal will continue from here.
I hope my screen is visible to all and I'm audible as well. Is my voice clear? Okay, so uh, hoping with that, I'm starting with the concept of backtracking and the problems. Uh, as Ayush discussed the backtracking idea, basically, in what backtracking is, we try and explore one possibility and then we undo the move we did previously. So, this is the generic backtracking template we talked of. Whether we try to choose one move and then we do the move, this part would do the move and then we unchoose it. Basically, we undo the chosen move. Let us get through it with one example. We have a lot of examples. Uh, so the classic example would be to generate subsets using backtracking, right? We talked of subsets. What are subsets? Talking of the formal definition of subsets, you might see the definition. Subset is a set or collection of some of the array elements where arbitrary places or indexes are like chosen. There is no such uh, condition to choose one index or not. So let me first take an example over here. Let us say this is the array. So I need to form a subset of this array, right? What would subset look like? Suppose we take the example array only. The array was 1 to 3. We need to form a subset. A subset might look like an array with 1, 3. It might be 1, 2. It might be an empty array as well. An empty subset is also possible. The null set. So subsets can be of this like. Uh, Let me give you the broad idea what we do over there. Uh, like when we talk of this index, there are two possibilities, right? Either we take this index on the subset or not. If we take this index in the subset, we include it in our answer, right? We include it in the subset. So there are two possibilities: if we include it or if we do not include it, right? So two possibilities for one index, right? So every index has two possibilities. This has two possibilities. This has two possibilities. This has two possibilities. Uh, so if we are familiar with the basic PNC, you might understand what this would look up to. So two possibilities for this in multiplication with two possibilities for this index in multiplication with two possibilities for this index, right? So this would account to a total count of six permutations, right? Or six subsets, basically. Uh, Sorry, not six, it would be eight, right? Uh, so there would be eight subsets, right? Okay. How do we do on, like, how do we code it up? This would be the basic idea for creating a subset, right? So how do we create it up? uh, let me first think of a state like in recursion or in backtracking. Basically, we think of in terms of states. Let me discuss with you what does state mean. Uh, let us say I am in this particular state, right? We would get a broad idea of what state is as we go through. So let us say this is a state we talk of or we require in the problem, right? Uh, and then we have some moves to do. This might be a move. This might be a move. This might be a move. This, and so on. There can be unlimited moves. Uh, and then we reach to this state using this move, right? We can reach to this state using this move. We can reach to this state using this move. We assume that we have previously created everything. We have sorted the things before this states, right? Uh, when we perform this set of move, when we perform this move, we assume that these things are to be sorted up. By these things, I mean the previous part is completely sorted. We have analyzed which moves do we want to pick up or not. And then when we pick up this move, we look for this state, right? So this is what recursion is basically. And uh, so backtracking adds a second layer to this concept, right? Let me change the color of the pen. Backtracking basically adds a second layer to this idea. When we reach for this state, right? When this state is completely looked up or this state is sorted, I mean, I performed all the moves or the operations I needed to do at this state. So I basically look out for this, or like I undo this move. I would like to undo this move and would like to reach up to this state again to look for the other possible set of operations. I might like to perform this operation. I might like to perform this move, right? So uh, this is what basic idea is. So we would like to extend this idea to a problem where we would like to create the subsets, right? So for creating subsets, how do we model the state for this problem? Uh, the state can be looked upon like this. Yes, so the state can be looking upon like this. Let us say this was the array. The state can be an index over here, basically. Let us say I am at index I. My index I is currently at this position. Uh, okay. And I've decided for this part of the array. Uh, I have already decided for this part of the array which elements I have to needed to pick for this subset, right? I've created a subset over here, and for this part of the array, I've previously decided from basically from 0 to index I minus 1. I have already decided which elements do we need to pick up in this subset. So now I need to decide for this element I whether I need to pick this element or not. So there are two possible set of moves, right? We pick this element, we do not pick this element. If we do not pick this element, we simply move on to the other index, right? Because this index is as well sorted up. If we do not pick this element, we do not perform any operation over here basically. So we move on to another index if we do not pick this element. If we pick this element, then there comes the thing, right? Let me change the color. Uh, if we pick this element, basically if we pick this element, we add it up in our subset, right? There might be some element added up before, like this one might have been in the subset. And if we pick two again, so like we added two here in the subset, right? And then we would like to look for the next index. We would like to look for the next state, right? So our next state would be this index. So when we go for this index, we have already configured this part of the array, right? From the element 1 to element 2, we have configured it previously. So we would like to do it for this index, right? So if we pick this element, if we pick the 3 over here, so we would be adding it up in our subset, right? So a subset would go like this: 1, 2, 3. If we do not pick it up, let me reverse it. If we do not pick it up, and like we move to the next state as we discussed, the next state would be the end of the array, right? There are no elements after it. So we essentially do not pick it up, right? So if we do not pick it up, we get another sub array or another subset, right? We are discussing subset. So we get this subset, right? 1 and 2. So basically, this is what a code must look like, right? We pick or not pick an element, and we have previously configured the previous indexes to a state, right? So and then we go for the next indexes or the next states. So this is what our code must look like. We have discussed the basic idea for it. Every element has two options to be taken or not taken. That's the idea for most of the subsequence or subset problems. You might try to code it out yourself. So like this was the core idea for most of the subsets or subsequences problem. Uh, so we would now try to look up for another example. Uh, Let us say we are given an array and we need to create permutations of this array. This is as well done with the help of recursion and backtracking. Uh, Let me take up an example and discuss it with you. Okay. Suppose this was our array. The array, let me change the elements for this: 4, 5, 6. A possible permutation for this array might look like something 5, 6, 4. There are other possible permutations, right? You can create as many as possible. Uh, what is a permutation? Basically, a permutation will have the same length as the array, as the original array, and all the elements would be randomly rearranged in it, right? So this is what a permutation is. Uh, so how do we approach this problem for the permutations? Anyone might like to give up an idea. Okay, so I will be discussing the core idea for this permutations. Uh, Now, as we thought of states previously, so what would be a possible state for this problem, right? What would be a possible state for this problem? Uh, Let us assume that we are at this index. We are at this index of the permutation. Basically, we have previously figured out which elements to be put in up in the subset in what order, right? Like, uh, let me take it up over here. Okay, so let us say we have created a permutation of three indexes. I am at this index. I am figuring out which element to be picked for this index, right? And I've previously configured for these indexes previous to it. So I've already like stored up elements in it, and I would like to like search for all the available options over here, right? By options, what do I mean? Uh, I would mean something like this. Suppose for the first element, for the first index, if I were to pick 6 over here, so for the second index, how many options would have been available over here? Among these three values, if a 6 is gone, I would be left with two options, right? 4 and a 5. So the amount of options is 2, right? So we have two available options over here. If we take a 4 over here at this index, or if we take a 5 over here at this index, right? Let me take up the cases with this 5 over here. A 5 over here would look something like this. The array, there was a 6 over here. There is a 5 now over here. What are the options available for this index? uh, for these three values, if we filled it up 5 and a 6, so we are left with a single 4, right? So we have only one option to fill it up. We do not have any more options, so we need to fill a 4 over here. So this is the end, right? So we reached the end of this state, right? When we picked up 5 over here. So this is what we go on for. Like if we pick up a 4 over here, what would have the array been? The array would look something like this. There was a 6 over here. There is a 4 now. Uh, Now there would be a 5 left only, right? So we will need to fill up a 5 over here, and we reach the end of this state as well. There are no more options. Like there are nothing more options, right? There are no indexes left in the array to be created. So what do we do? So like if we have already figured out for these options in this state, right? We were looking out for this state, right? So if we had figured it up for this state, so we need to backtrack, right? So we would backtrack. We would like to undo this move and count it as a permutation, right? We count it as a permutation as this was possible. So we backtrack it and undo this move. Similarly, for this move, when this was formed, we reach the end of the state, right? So we backtrack it from here and we undo the move. Basically, we undo the elements, place it over here. So if this state is all sorted up, like if this index, we already figured out all the possible options for this. So we would like to undo this move as well, right? We would like to backtrack and like change the options for this index, right? As there was a 6 over here, we place a 6 over here. Uh, we could also place a 4 over here, right? Or a 5 over here. So we would like to look out for other options as well for this index. And then we would like to traverse again the entire array and figure out the options for the array again. So this is what a backtracking involved with recursion would look like something. Uh, and for this problem, the state would be something the similar, right? The indexes. And you also need to check which options of the elements we can fill it up for this index if we have already filled up the previous indexes, right? So let us first discuss the solution code for this, and then we might figure it out the entire idea again, or look up if we have any problems. So we go to the slide. This was the array given to us at the input. These are the possible permutations for it: 1, 2, 3, 1, 3, 2. Uh, so like we visit every unvisited number for each index. Index was our state. For each state, we visit every unvisited number previously and store them, and we go to the previous state, or we backtrack basically. So we have already discussed the idea. We would now like to look to the code. Uh, this is the basically code for the recursive thing. This was the array ARR, and this is the current permutation. And this is a visited array to look for the elements we have already stored it up in the previous state, right? Uh, like when we were at this state, or let me clear things up. Uh, when we were at this state, uh, how do we figure it out? We need to put up a 5 over here, or we were left with the option of filling up 5 only over here, because we knew that we have already put up a 6 and a 4 over here. So there were no operations, there were no options left with us, right? We're only left with a 5. So we need to figure it out what values we have put up over here, right? A 6 and a 4. What values we have covered till now? What values we have visited basically? So I need to create a visited array for the state, right? Okay, so this would be the visited array for the state. How many options are possible for this state? And this would be the current permutation we are creating. This is the input array. So if the current dot size, if the current permutation size is the same as the array size, so what do we do for this? Uh, we we basically add it to our answer, right? Let me first show you this. Like if we have basically figured out the entire permutation, we are at the end of the permutation basically. So we are at the end, means we have figured out for this last index as well. We are at the end. We do not have any like suitable indexes to put upon. So this permutation is entirely created, right? So we store it just in our answer. Answer is a vector, you could say vector of vectors. So and then we return from this. We do not have any available options to put upon as there is no suitable index. So we just backtrack, right? We go like there was no option over available over here, so we go to the last index, right? So this is what it is doing. Uh, if if we are at an if we are at an index, we need to look up for the available options, right? So we look up for the entire array, which elements did we previously pick up and which are available to be picked up. So we go through the entire array. If this index is visited previously, uh, let me discuss it. Like if this index is visited, if the element is visited, we would like to skip it, right? We do not want to create a permutation with repeated elements, as there is no permutation with repeated elements, right? A permutation handles only unique elements, right? So this is the definition of the permutation, right? This line would mean. So we skip the visited elements, previously visited elements, and then we would then this is the move we are performing, right? We mark this element as visited and we store it in our answer, right? Like we have stored it in our current permutation, this element, and we mark it as visited for the future states. And then we go to the next state or the next index to be look upon. So uh, we figure it out for the next state as well. So what do we do is we go to the next state, right? ARR current visited as it is. So we go to the next state then, uh, and then what we look for is we go to the next state and then we undo this move. How do we undo this move? We added a index, right? We added a new element in our current permutation. So we can undo the move by removing this element, right? So we pop out the element from the current permutation and as well mark it as unvisited, right? If we are undoing the move, we would like to mark it as unvisited for the for the backtracking purpose, right? Otherwise, it might create some errors. Like I let me discuss this as well. Uh, like if I'm done with this possibility, right? Not this. Okay. If this was the array, I am at this index specifically. There were two options, right? If this was a 6, there were two options, 5, 4. Uh, if I explode 5 completely, and I do not mark it, and I do not unmark it as visited, so this would look up like the 5 would still be visited for this, right? For this move. But if we were putting up a 4 over here, we would need the 5 over here, right? So this would create us problems if we do not unmark it as visited. So remember always this, we would like to completely undo the move. So this was the move, we completely undo it. We added an extra element, we removed it. We marked it as visited, we unmarked it. So this would be the move unduation basically, or reverting back to the previous state. Uh, this would be the complete idea for it, for the problem. We would like to look upon the next problem, combination sum. And then we have the classic and queens problem. So what does the problem statement basically says? We are given an array, right? Candidates array, or you can simply take it as an array, right? So we are given an array. We are given a target. We need to perform, like we need to return the subsets. Uh, Basically, subsets in this subset, there can be multiple elements, right? We can take up an index multiple times. Uh, two was taken two times, right? In the array, it was only two. It was array. In the array, it was only once, right? So we take up a two twice over here. So we can take up any element more than once, right? So we need to return the subsets with this sum as the target, right? So 2 plus 2 plus 3 gives me 7, and a 7 alone would be required. So we need to return all the subsets, or we need to create such arrays. Uh, so how do we go for this? Anyone has any idea for solving this problem? Okay, so I think I might need to discuss it. Uh, Let me take up the input array only. Example array 2367. Okay, okay. So this was the array 2, 3, 6, and a 7. And we are given with a target, right? So how do we solve this problem? The target was 7 for this. Uh, like, uh, how do we get the idea of recursion or backtracking over here? Uh, it does not come out of a moon, right? So how do we get the idea for recursion backtracking over here? Like this would be a simple, like you need to get the idea of recursion and backtracking everywhere. Uh, when the problem itself says you need to explore all the options. Uh, what do I mean basically is, for creating a 7 as the target, we would like to explore all the options we can create, right? Like we can take up two twos and a 3. So this would have come by exploring all the options, right? If we could have taken another 2, like if we could have taken two, like 3 twos, and then we were left with no option to take up an element. So this option was like cancelled out, right? So we needed to explore all the possible options, right? So if we were to look up for all the possible like options at any stage of the problem, so that is a basically recursion or backtracking concept, right? So we get the idea of recursion. Uh, so how do we create a state over here? How do we model the state for this problem? I would love hearing it from you guys, or I might discuss the idea. So the idea would go something like this. Okay, the idea would go something like this. Uh, let's say, uh, okay, let's say I have a specific uh, target to be reached to. Okay, or basically coins, a target do we want to reach to, uh, and we are at an index. We are also like the current state would contain the target and the index we are at now, and the index we are at now. So let me go to the array. Okay, let's say we are at this index, and we have explored all the possible options for this, right? For the previous indexes. Like it might be like we have taken up a 2 over here from this, or like no twos at all. So we have explored all the possible options over here in this. So uh, and we would like to figure it up for this index, right? What options we can take it or not. So like there are two possible options, we can take it or not, right? So if we take it, like if we would like to take it, we would like to add it in our array, right? So so we would like to add a 3 over here. uh, so what would the next step would do after taking it up? Would we switch to the next index or the next possible indexes? No, we might like to we might like to add the element again, right? So we might want to add the element again for this after adding this index, after adding this value once, we might we would again go back to this index as the state. and with a reduced target now, because the target initially was 7, we picked up a 3 over here. So 7 minus 3 gives me 4, right? So now we have to prepare 4 coins from this array, basically 4 coins from these elements. Uh, so we go back to this element again. So we are at now this index again. We might want to pick up a 3 over here again, right? Or we might want to continue with only one 3. So we would like to skip it if we do not pick it. So if we do not pick this 3, we would like to go to the next index. We would like to go to the 6 over here. If we pick it up again, we would like to go to this 3 again, right? For the possible set of operations or the options. So if we go to this 6, uh, if we go to this 6, we might want to add it or not. This is a common, right? Like the target is a 4 over here, and we would not like to add a 6 because it would outcome, like it would overcome the target. So we would like to skip this index and go to the next state, right? So our next state would be this index 7, and the target would be 4. We would again like to skip this because the value of the coin is much larger than the target itself. So we would go to the end of the array, and eventually we can figure it out if the target is all created up or not. Like if the target uh, at the end of the array is a 0 or not. So the target is left, right? We are left with the 4 coins to create. So we did not create a possible set of array, right, for the target. So this was completely wrong move at all. So we need to reverse it, right? So we need to backtrack it basically. So uh, we would then backtrack it from here and then look for this index again. Uh, and then we were left with no options, right? So we would like to backtrack it again over here for this index. So we were again left with no options to create a 6 over here or to put up a 6 over here. So we would like to backtrack it again for this 3, right? So we can add a 3 again over here as the target is still greater than this value, right? So we would like to add a 3 over here again and look for all the possible set of options we have, right? So if we added a 3 over here again, uh, we again reach out to the same state, right? uh, like I might want to add a 3 again over here, or I might want to skip this element now, right? So if I skip this, I would go to this index. The value is greater than the target, right? Our target would reduce now, right? For it would go to 1, right? Because we added a 3 over here. So we go to the next index now. Uh, the 6, if 6 is possible or not. So we we cannot add a 6 over here, right? Because our target is a 1, and we cannot add a 6 over here. So we would like to skip this index as well. So we go to this index. We cannot add a 7 as well because our target is 1. So we would go to the end of the array, right? We would reach the end of the array. So if we reach the end of the array, we must ask ourselves if we completed the target, if the target is a 0 or not. If the target is not a 0, we did not create a possible set of operations, right? We did not perform all the correct operations and create up an array. So we might want to backtrack again. We might want to reverse all the operations or undo all the moves we did. So we would like to undo the moves, right? So uh, we reach the end of the array. So we would like to look up for the 7 if we have any other possible set of options or not. So we do not have any option to add a 7 over here. So we again reach out to the previous index for some options left. So we do not have an option as well over here. So we would like to go to this index. So we reach out to 3 itself, right? If we can add a 3 over here, can we? No, right? Because the target is a 1 and we cannot add a 3 over here. So we would again backtrack it to the previous index. So we would go to 2, right? So we cannot add a 2 over here, right? Because it would overcome the target. So we would go to the start of the array. So like our recursion stack is completely completed, right? So there are no possible set of moves with possible set of arrays we can form with 2 3s, right? So this would be the entire intuition we can get, or the entire uh, idea we can think of for the problem as a state. So this is how we model the state of the problem. We would like to look up the with the code for this problem. Uh, so this was the problem that were asked, uh, and then we would like to discuss the solution for this problem. This is the input array ARR, and this is the target we need to complete, right? So we create a current vector, a temporary vector, basically a data structure that would store the current array we are forming, right? So we pass on to the current. It is completely empty right now, as we have just created it, and we don't add any elements because we would now look for the array elements, right, to add it. So we will be looking it for, and we pass on the input array as well, the target and the index, right, we are at. So we have also created an array of vectors, right, to store up the answer array. So we pass on to this function, this recursive function, uh, this index. This is the index, one of the state like parameters, and this is also one of the state parameters at target. So this index and the target is the complete state we are discussing over here, right? So if the target is zero at any time, uh, let me take up this over here as well. Uh, Suppose a given array was, let me take up the initial array itself. Suppose our given array was 2, 3, 6, 7, right? This was the array given to us. So uh, if we had already formed a suitable combination for it, like if we had already taken up two twos and threes and a single three by this stage, uh, I might not want to go to this index, right? Because we have already created an array, right, for this. We have already created a possible combination of the elements for this, right, for the target. You can look up the target is completed, right, the 7 over here. So we might not want to go to this because this would be a waste of time, right? The target would be 0, and I would not be able to add a 6 over here in this array, right? And I would not be able to add the future elements as well. So this would be a completely waste of recursion space, right? So what we do is whenever we reach to an state, if a target is 0, so like our task is already completed if the target is 0, right? So we would like to backtrack again. We would like to return to the previous state and then like completely end it over here. So we would like to reach out for the next set of moves we can perform at this index, right? Will I be able to add a 3 over here again? No, right? Our target is again 0. So what we will do, we added a 3 over here, right? So we would like to remove this 3 and look out for the next index, right? Because we added a 3 over here. So we would like to undo this move, right? So we would now go for this 6, right? If we can add it or not. So if we go for this 6, can we add it in our array? The target would be now reduced to 3, right? Because there is a 4 over here forming up in the array. The target would be 3. Uh, we cannot add a 6 over here, and we cannot add a 7 over here as well. So this is how the code works actually. So if the target is a 0, we form the pruning, right? We perform the pruning. Pruning is an important concept in recursion. Like it helps in reducing the time complexity by like it can help in reducing the time complexity by larger amounts, right? Sometimes pruning might make the difference between an accepted code and a time limit exceeded code. So you might want to look out for pruning in most of the recursion problems. Uh, if the target is 0, we would like to like add to our answer vector the current and array we have created, right? So we are adding to the answer vector the current array we have created. So and then we return to the previous states, right? Uh, so if this is the end of the array, so like this condition is for the end of the array, right? If we are at the end of the array, or if the target is less than 0, basically if we have put in up some wrong cases, right? Like uh, Let me take it up. Like there was a target 3, we needed to fill it up, and we put up a 6 over here. So what is the sum of this array right now? This would be 10, right? And we need a target of 7. So this would be, so the target would be reduced by minus 3, right? 7 minus 10 is minus 3. So we already over satisfied the target, right? So we would like to remove this, or the next, or the next couple of recursion calls, including this state, would be a complete waste, right? Because this addition was a complete waste, right? This 6 we added over here, we would like to undo this move, right? Because if we added a 6 over here and we move on to the next index 7, do you think we would be able to perform a suitable array if we reach the end of the array? Like at the end of the array, we have to ask ourselves, right, if we performed a suitable combination of elements or not. So we would not be able to perform it if we over satisfy the target at an early stage, right? So we need to prune it over here as well. So if we added a 6 over here and the target is over satisfied, we would like to prune it in early, and we would like to exit to the previous stage or the previous state, right? So this is how what the pruning concept works over here as well. So let me take up the code again. Uh, this is the base case or the pruning, right? Uh, and then we would like to take the current element and explore all the possible options we have for the next state, right? So if we take up the current element, we would like to push it up in the current array, right? uh, this is what is storing up the entire array we are creating, right? So we add it up in our current array, and then we model the state, right? We model the state for the next set of problem. We picked up at the index. So what do we do is we go back to the same index so that we can put the element at that index again, right? If we wish to. So we go to the same index, and our target is reduced by the ARR value of that index, right? So we pass on the other array elements, right, again, and then we backtrack it to the previous state, and then we wish to backtrack this, right? We performed a move, and then we would like to undo the move, right? So how do we undo the move? We would like to uh, we would like to remove this element, right? We would like to reduce this element or remove this element basically, if we wish to undo it from the current set, and then we go to the next state, right? Our next state would be like if we were to skip this element. So if we were to skip this element, we would go to the next index, because we would not be taking it up in the like future cases, right? So if we are skipping it, we would not be able to take it in the future uh, possible combinations. So we skip this and we go to the next index, and the target would remain as it is, right? If we have skipped it up, we did not take it. So the target is not reduced by anything. So this is what the code would look like. Uh, and like if we perform this set of operations, if we reach to a suitable uh, current vector forming up, the target is 0. So we would like to add it up in the answer, right? So this is what it does completely. Uh, so this was the problem we discussed over here. I hope this problem is clear. The modulation of the state as well. Do we have any doubts? I don't think any doubts coming up. So I would like to move on to the next problem. So if this problem was clear, so we go to this problem, right? The takeaway. I think the takeaway slide should be at this state, at this stage. We go to the next problem basically again. This is a classic problem, n queens, and like if you understand this problem, if you were able to understand this problem, it would create a lot of backtracking concepts, right? If we were to understand this problem. So, what does the problem say, right? There are n queens. Let me take up the board. Uh, I think some of you might have been a chess player or something at any stage. So, a chess board is basically an 8 cross 8 board, right? Uh, So what I'm creating is let's say we have an imaginary chessboard of 4 cross 4 size. Uh, 4 cross 4 chessboard, and we were given with 4 queens. 4 queens. Let's say we have 4 queens to be placed up at this chessboard, right? So we are given with 4 queens, and we would like to place the queens in such a configuration that they like 2 queens do not attack each other. So like all the queens are at a safe distance from like others, right? So no 2 queens attack each other basically. So like we might want to place a queen over here. Uh, we might want to place a queen uh, over here, right? Uh, over here. No, not over here. Uh, like you can figure it out or check for all the combinations if you wish to. So like you can go it up for this. Uh, so what we do, we are given with some conditions or some restrictions to place the queens, right? So uh, we need to check for the queens don't attack each other, right? So what are the possible set of moves a queen can perform? Uh, let's say if this cell has a queen in it, it can go straight right. A queen can go up ahead or bottom right. So it can also go for this uh, direction, right? Straight left and straight right. It can also look up for the this diagonal, right? And this diagonal as well. Uh, this diagonal and this diagonal, right? So queen can move up in 7 directions or 8 directions. Sorry, if you have some basic idea of chess, queen can move up in 8 directions, right? Uh, an horizontal and a vertical direction along with 2 diagonals. So if no 2 queens should attack each other, we need to check here. We need to check if like if the 2 queens share the same move, right? Like if I have a queen over here, right, in the same horizontal level as this queen, so they might attack each other, right? Because they share the same set of moves. They share a common move, right? This queen can attack in this direction, and this queen also can attack in this direction, right? So they share a common set of move, right? Uh, or if we can place a queen over here, we cannot place a queen over here as well, right? Because this queen might attack it in this direction, right? So we need to look up for the possible set of operations, right? Possible set of options, basically. Uh, so as the term options comes up in our mind, we might want to look up for the idea of recursion, right? Recursion and backtracking. So this is how the idea of recursion or backtracking comes for this problem as well. Also, like we did not mention up the constraints over here. The constraints of the problem also creates a idea which algorithm should we use or not. So, like for recursion and backtracking, generally the constraints should be a pretty smaller, uh, like or else like if DP is not involved in it or something like that. So, like this is what the idea would be. So of the problem. Let me discuss the solution of this problem or the idea. How do we do it? Basically, we explore the every possibility of placing a queen right. So, and then we check its safety with the other queens we have placed previously, and then we go to the next row and repeat it. So, let me discuss the state with it. How do we model the state for this problem, right? So, let me go to the chessboard. Uh, let's say I'm figuring out a place. So let me discuss this thing with you. Now I think you might be able to understand. Like I think you might be able to observe a single thing. Uh, we would not be able to place uh, 2 or more queens in a single row, right? In a single row and in a single column, because if we place 2 or more queens in a single row, they might attack each other. So this is not a valid configuration. And if we place two or more queens in the same column, so they too might attack each other, right? So this is not a valid configuration. So we do not have a we do not have more than one, right, more than one queen in a single row. So what we can do is we can have the row we are processing right now in our state, right? uh, if we were to create up a state for this problem, uh, let's say this is the state. One of the indexes would be like like the row we are processing right now. So let us say we are processing this row. We are figuring out the options to fill up queen in this row, right? So we all know, right? We can fill up a single queen for a row, right? So if we are looking up for the options to fill up for this row, we would like to figure, like we would, or like we would like to have figured it out already for these previous rows, right? So that we can check the queen safety. So like if we have placed a queen over here previously, if we have placed a queen over here, like this would be a valid configuration up till this now, up till this part of the. Let me change the color over here. Uh, like up till this part of the board would have been figured it out completely with a valid set of possible configuration for the queen. So we now look to place a queen over here such that it is completely valid till now, till this part of the array, till this part of the chessboard, right? So we have figured it out for this part of the board previously. So we now need to look up for this index, right? For this row, basically. So how do we think of its safety? Like I might wish to place a queen over here. Let me take out this color. Like I might wish to place a queen over here in this column, right? In this row and in this column. So uh, how do I check for its safety for this basically column? Uh, I might like want to check for the queens attacking to it. Basically, is this queen attacking it somehow? No, it does not share the same column or the same row, as well as the diagonal of this queen is not shared with this queen, right? So this queen is not attacking it. Is this queen attacking it? No, right? This queen as well does not attack it because it does not. These two queens does not share the same row or the same column or any of the diagonals, right? This queen has the diagonals going like this. This has the diagonals going like this. So they do not share the same diagonal as well. So I might want to place a queen over here as this is a valid configuration, right? And then if this is a valid configuration, we can perform at this row, right? So we would like to go for the next row to be figured out. So what we will do is we will go to the next row and we would like to figure it out a possible uh, option for this row for the queen to place in this row, right? So I would like to place a queen in this column. Is this possible to place a queen in this column at this row currently? It is a no, right? Because we already have been placed a queen at this column, right? Previously, you can see it over here. So we do not have a case to look up for this column, right? So we would like to reverse it and we have to backtrack, and then we would like to look up for this index or this column, right? Can we place a queen over here for this column? No, right? Because these two queens share the same diagonal, right? These two are at the same diagonal. Uh, and I think these two queens are at the same diagonal as well. So these two queens at the same diagonal as well. So there is a lot of like these two queens are also at the same column, right? So this is not a valid spot completely. So I might want to reverse the move we performed here. So I will have to look up for this option, right? I will have to look up for this option if we can place a queen over here. So we will now look for the safety of this queen. Uh, Let me change the color of pen. Okay. So is this queen attacking it? Uh, I think no, right? this queen is not attacking it. This queen as well is not attacking it. Uh, do not share any diagonals or any horizontal or vertical lines. This queen and this queen as well. So this is a bad configuration, guys. We have figured out a bad configuration. And if we have figured out a valid configuration, we would now like to move on to the next state. How do we like our state was right? Like our state was the row number, right? We were figuring it out for. So we would go for the next row. As we reach the end, like as we reach the end of the board, as our board is as we have reached the end of the board, so our board might have been configured all completely right. So we have completely placed the n queens such that they do not attack each other. What do we need to do at this stage? So we need to add the board. We need to add the board or the combination of the queens. Basically, the configuration of the queens. We need to add it up in our answer vector, and then we need to return it. Right. We need to undo this move, and then return to this index. Right. So we would be at this index, and then we would look for other possible configurations which we can place a queen over here. So this set of move would be completely removed. Uh, so this set of move would be completely removed, and then we would look for another combination if we can create it. So we we placed a queen over here previously, and this was a wide configuration. So we will look for this configuration as well. If we can place a queen over here, we cannot place a queen over here, right? Because this queen will attack us if we place a queen over here. So this is not a valid configuration to place a queen over here. So we cannot. So we will not reach the end of the board, right? So we do not have all the queens figured it out. So we would like to backtrack again to the previous row, as this row is completely completed, right? This row is completed. So we would like to backtrack to the previous row and go to this row. And we would like to undo the move we performed at this row. Uh, like we placed a queen over here at this row, right? So we would like to remove the queen over here and place a queen over here and look for its safety. So we placed the queen over here and we will now try to check its safety. If this is a valid configuration to place a queen over here in this row. So this is not a valid configuration as you might see it. We have already placed a queen in this column, right? So this is not a valid configuration to be looked upon. So we now try to check up for the next column, right? So we try to check up for the next column. And also like if we backtrack to the previous state, we would also remove it, right? We would also remove our moves completely. So we undo the moves completely. So we're at this stage, right? So I would like to place a queen over at this state. Can we place a queen over at this state? No, right? Because this queen might attack us if we place a queen over at this state. So I would like to look up for the next option, right? So this option, we cannot place a queen at this option as well, right? So now what we will do, we'll try to backtrack to the previous row, right? So okay, we will try to backtrack to this row and look up for other options as well. So this is how the backtracking idea would work if we model a state like this. So our state modulation is completed, right? We completely decided how the state would move on. And one important thing remains over here is how do we check the safety of the queens, right? Like if we place a move, like if we place a queen at this row and a column, so how do we check the safety of this queen over here? So we need to track if we have placed a queen in this column already or in this row. Like row needs not to be checked, right? Because we would only be placing a single queen at this row. So we will need to check it up for this column as well as the two diagonals, right? These two diagonals we need to check it up for. So how can we do it up in in an optimized and minimized manner? Uh, like one might think up of creating some maps, right, or some hash arrays of three hash arrays basically for this column, for this diagonal, for this diagonal. Basically, that would store up a lot of space, right? That would be completely messed up code, uh, creating three arrays. So uh, we will be discussing the optimized manner of checking it up for this queen, right? Uh, what we can do is, mm, okay, let us move to the board again. Uh, okay, what if we can create an array? What if we can create an array of rows? And like if we're at this row currently, if we are figuring it out the options for this row, we have already placed some queens at this row, right? And this row as well. So we can create an array of rows, and then we might like to add the uh, column we have placed the row. We might like to add the column we have placed the queen at for each row, right? Like this was the second column, so the second column for the first row, the fourth column for the second row, right? Okay, the fourth column for the second row, and then we are at the third row currently. We would like to process all the moves or the options we have at this row. So when we are at this row, we need to check up if we have already placed a queen in this column, right? So like if I were to check up for this column, uh, the column number is 2, right? So a 2 would appear over here in these previous rows, right? A 2 would appear over here in this previous rows if it was already placed, right? If a queen was already placed in this column. So a 2 would appear over here if it is already covered, right? And for the diagonals part, how do we check up for the diagonals part? Like if I were have a queen over here, like I might have a queen over here previously, set it up, ignored this now. I might have a queen over here at this part, and I've stored the information right for the column and the row. So and for diagonals, uh, we can do one thing. Okay, I need to check the color. Like what we can do is we can track the absolute differences between the rows and the columns, right? Like this column is 2, this column is 4, right? This column is 4, and the row number is 1. So 1, comma, 4, right? And uh, this this would be uh, 3, comma 2, right? So we track the absolute differences between the columns and the rows. So the absolute difference between the column numbers would be 2 and a 4 would give me a absolute difference of 2, right? So and the absolute difference between the row numbers would also be 2, right? So if the absolute difference is same, we are on the same diagonal, right? We share the same diagonal. So if we share the same diagonal, we cannot place a queen over here. And like this was quite intuitive as well. If we could look up for that diagonals, right? Uh, like the diagonals over here share an angle of 45-degree with the horizontal, right? So 45-degree or 135-degree, 45-degree or 135-degree does not matter over here because we are looking at in the same thing, right? We need to check up for the diagonal. So we check it up completely, like we check it up for both the cases together, right? So the absolute difference between the row and the column must be the same to share the same diagonal by the queen. So this must be the condition for diagonals, right? And we have checked the columns. The column number should be there in this array, right? So this would ensure the safety of the queen. Uh, so we look out for the possible combinations for this, possible options for this, and then if we get a possible configuration to place all the n queens, we just store it in our answer. So this is how the problem would completely look like this. So is there any doubts with this idea? Okay, let me discuss the code now. Okay. Uh, we are given an integer n, basically an n cross n chessboard is there. Uh, n is not restricted to be 8, so the size of the chessboard is a variable. So then we track of the then we keep a track of the columns we have placed at the previous rows, right? So this would be the vector we have created to keep a track of the columns of the rows we have already placed. So placed is a vector for the track, for tracking it up. And then this would be the vector for showing the answer, right? For a valid chessboard, we have stored it up. So then we go to for the state, right? So we go for the zeroth row, or the basically the first row uh, in our chessboard. If the row is so we go for this row, the first row, and then we also store it up in the placed, right? We pass the placed area as well, because we need to store it up in this as well. And then we also pass the answer vector of vectors. Uh, like if this like if the row is completely at the end, right? If we are at the end of the board, so we already figured out a possible configuration to set up the queens, right? So we just add it in our answer. So like this is the addition part of the answer. We just added the combinations of this in the answer. So like you can simply check it out, how do we add it. If we placed at this state, we just replace it with a q, or if we did not place the queen over here, we replace it with a dot, basically for an empty uh, chessboard square, right? So uh, now we look up for the options we have for this row, right? So the number of options we have for this row would be equal to the number of columns, right? So like if I was at this row, I was looking to place a queen over here, a queen over here, a queen over here, and similarly a queen over here, right? So there were four options to place a queen over here in this row. So we we are like we have the number of columns as the options, right, to place up for in a row. So we iterate for each option. So we iterate for each column over here, and then we ensure the safety of the queen. Like if we want to place a queen over here, we ensure the safety. We mark the queen as safe initially, thinking of like if we encounter any unsafe conditions, we would like we would false it would set it to false later. So we then iterate to the previous rows previous to this, right? So this is what we discussed, right? The row is the current current row index, right? So we iterate from the previous for the previous rows, and then we look up if the column number, if this column is the same as we have placed for each for like any of the previous rows. If it is the same, we have already placed a queen at this column, right? So this should ensure we mark the safe to false, right? So this will ensure if we will mark the safe as false. And then we also need to check for the diagonals, right? Diagonals, I think I gave you the intuition for the diagonals, right? If the absolute differences between the rows and the columns is the same, we have another queen with that same diagonal, right? So if the absolute difference between the column between this column and the and any column at any index before at any row index before is the same absolute difference between the rows, right? So this would ensure that the queen is not safe. And if the queen is safe, we place a queen over here. We mark this row. We mark this row and this column in the placed array, and then we go to the next row. Right? We go to the next row. We pass on the placed array itself, and then we also pass on the answer. So if this queen is safe to be placed over here, we pass on to the next state. And if not, then we return it. We simply return it if not. So this is what the code would look up. Uh, and then what would the time complexity be? The time complexity would simply be n factorial, because why, like, one question it might come up to you, why the time complexity did not go up to n to the power n? Uh, because we did discuss in the idea of backtracking, right, or in the recursion. Uh, I think it was this slide itself, or this one. Okay. Uh, yes, this was the slide I was referring to. The number of choices to the power of depth of recursion, right? So for this problem, we were iterating for each row, right? For each row. So the depth of recursion would be for each row completely. So the depth of recursion would be n, right? So the depth would be n, and uh, so the depth would be n, uh, not n basically, n cross n, right? We were creating a state of the rows and the columns, right? N into n, the depth would be the depth of the recursion, and then what we did was we were looking up for n possible the time complexity should have been this instead of n factorial. So how does the n factorial come in the first place? Uh, the n factorial comes from the idea of pruning, from the idea of checking its safety, right? Like we were not completely going up like any random state for all the n in like for all the n cross n states we're not iterating for, right? We only iterated for up to a specific number of sets or the states. So not all the states are being processed. So the time complexity would reduce down and go up till n factorial only. So we explored all the possible cases. N factorial is a huge time complexity. So for smaller n, this code will run. Uh, so we so let us discuss the takeaway of this session. Every recursion problem follows state, base case, transition. And then to add over here, you might as well add some pruning statements if if you wish to. And then we also return the final answer for any recursion problem. Uh, for backtracking, we basically have three possible states: choose, explore, and undo. So this is how we solve a problem, right? We model a state and then we go to the base case transition and we return the final answer simply for recursion. So this is the end of this session. I hope everything is clear up till. So if you have any doubts, you can ask here, or if not, you can leave the session. So the meeting is over, guys.